Hello friends, I am Dr. Nilesh Dani, working as a lecturer, Mathematics, Government Polytechnic Rajkot. We are in the series of lectures for Diploma Engineering Semester 2, Advanced Mathematics, Group 1 and Group 2. As you know, we are discussing differentiation and its application, and we are in the 7th part of this discussion. So far, we have seen various aspects of differentiation, concept regarding that, some examples we have solved, and we have seen the second order, that is successive differentiation also. As we know, whatever we study, we generally study for application purpose of that. So today we are going to see what is an application of differentiation, because differentiation, as we have seen earlier, is a rate of change in one variable with respect to another variable. So whenever there is a change in one variable, there is a change in another variable. Also, we have seen that geometric meaning of derivative is slope of a tangent at a particular point. So these are two aspects we have seen earlier. So today we are going to see the application where the concept of geometric concept of tangent will come in the picture. Before we start our lecture, let us have a brief look on what we have seen so far. We have first defined derivative. Derivative is a limit h tends to 0, fx plus h minus fx upon h. The process of getting derivative is called differentiation. We have seen some formulas regarding this: derivative of x raised to n, e raised to x, a raised to x, log x, sin x, cos x, tan x, cot x, sec x and cosec x. Also, we have seen working rules. That working rules are used to get derivative of addition, subtraction, multiplication of two functions, as well as division of two functions. So whenever we have addition, subtraction, multiplication or division of two functions, and if we want to get derivative, we use these working rules. Also, we have seen chain rule, which is used to get derivative of a composite function. So composite function is a function is a mixture of two functions, or one function is operated on another function. This is chain rule, where dy by dx is dy by du into du by dx, where y is a function of u and u is a function of x. So it is a composition of two functions y and u. Then we have seen the derivative of implicit function. Implicit function generally denoted as fxy is equal to 0, where the equation is differentiated directly with respect to x and we solve it for dy by dx. Then we have seen that derivative of parametric equation, that is dy by dt upon dx by dt. Also, we have seen logarithmic differentiation. So whenever we have a function that is of the form fx raised to gx or gx raised to hx, means the base and power both are function of x, we use logarithmic differentiation, for which we take log both sides first and then we take its derivative. Then we have seen successive differentiation, that is derivative of one function more than once. Generally we confine ourselves to second order derivative, that is d2y by dx2, that is derivative of dy by dx with respect to x. These are the things which we have seen so far. Today we are going to discuss one of the application which is known as maxima and minimum, which is to find the maximum value or minimum value of a function. always we are interested to maximize certain thing or minimize certain thing. For example, in an industry we generally want to maximize our production, whereas we generally want to minimize the cost of the product. So if we want to get what is the maximum and what is the minimum, we can use the differentiation. So let us see. So for a function y is equal to fx, to find the value of x for which the function is maximum or a minimum in a small interval. These maximum and minimum are not absolute maximum minimum, but they are local, means in a certain interval the value is maximum, or in a certain interval the value is minimum. So this is the concept of local maxima and local minima. Now let us see what is maxima and minima. This graph is a graph of a function y is equal to fx, where the points in red color gives local maximum point, and the points with blue color indicates the local minima point. So at red color point the function is maximum, and at blue color point the function is minimum in the interval. Now the question is how to get these points. Here in the figure there are 5 points at which the function is either maximum or minimum. So first we'll see how to get these points where the function is either maximum or minimum. Then we'll see at which point out of all those points, at which point the function is exactly minimum or maximum. For that another test is there, so we'll see. So let us see how we can get the maximum value and minimum value of the function. So these are the steps to get the maximum value and minimum value of a function. The first step is to find the roots of f dash x is equal to 0. So we find the derivative of fx at f dash x, and we find the roots of f dash x. Let us say these roots are say x1, x2, x3, like that. As we have seen in the figure, there are 5 points in the for which f dash x is equal to 0. So here we will get certain points where f dash x is equal to 0. These are the points where either the function will be minimum or maximum. So let us see how to get at which point the function is maximum or minimum. So this is second condition or second step. To find f dash x at x1, x2, x3, at these roots we will find the value of f double dash x. F double dash x is second order derivative of fx with respect to x. Now if this value of f double dash x is less than 0, means it is negative, the function is maximum for that xi. So if I take f double dash x1 and if the value is negative, then I can say that function is maximum for the value xi, or at xi the function will be maximum. And if the value of f double dash x is greater than 0, then we can say for that xi the function is minimum. So these are two conditions. Out of these obtained xi's, we will find the value of f double dash x at these points, and out of that, if the value is negative for these xi, we can say at that point fx is maximum. And if the value is positive of second order derivative, we can say that the function is minimum at this point. Let us see the figure. This is a graph and this is a maximum point. So here the slope is 0, and as we have seen, slope indicates derivative at particular point. So we have taken f dash x is equal to 0. So if we take f dash x is equal to 0, we obtain this point. The root of that is this point. So this is why we are getting f dash x, roots of f dash x is equal to 0. Now you see here the slope of tangent is positive, here the slope of tangent is negative. So from positive it becomes 0 and negative, so that way it is a maximum, local maximum. Now you see, if the function is increasing, then its slope is positive. So if f dash x is greater than 0, then the function is increasing, and as you know the slope is decreasing here. From positive it becomes 0 and negative, so we take f double dash x is less than 0. Now let us have another this here. For the maximum, this f dash x is greater than 0, then it becomes 0, and then it becomes less than 0. Whereas for minimum, f dash x is positive, then it becomes 0, and then it becomes positive. So here we see that the slope from negative to 0, positive to 0 to negative, so it slope is decreasing here, means we have f double dash x less than 0, and here the slope is positive to 0 and negative, means it is decreasing, so f double dash x it is from negative to 0 to positive, means it increases, so f double dash x is greater than 0 for a minimum point. Now once again here this is a maximum point, so here slope is 0 and we have d2y by dx2 or d2y by dt2 is less than 0. If this is minimum, then also here derivative is 0, so we have a root of that is this, and the second order derivative at this point is always positive. But if second order derivative, say dy by dx is 0, but second order derivative is also 0, we can't say the function is either increasing or decreasing. This is a situation. Generally we are not discussing this case C, but if this comes 0, we can't say anything about its increase or maxima or minima. We can't say the function is maximum or minimum if second order derivative is 0. Now let us see some of the example based on this. We are given a function fx is equal to x cube plus 3x x cube minus 3x plus 11, and we want to get the maximum and minimum value of the function at this. Now here first we'll find first order derivative, that is f dash x is f dash x. First we find the roots of f dash x is equal to 0. That are the points where either the function is maximum or the minimum. So let us have a look on the slide. That is, we have find out f dash x, that is derivative of x cube is 3x square minus derivative of 3x, that is 3. Derivative of x is 1 as we know, so it is, and derivative of 11 is constant, so it is 0. So derivative of 11 is 0. So f dash x is 3x square minus 3. Now we are interested in the root of this, so let us take f dash x is equal to 0. F dash x is 3x square minus 3, so 3x square minus 3 is equal to 0. Now taking 3 common, we have 3 into x square minus 1 is equal to 0. So we have x square minus 1 is 0, so x square is 1, so x is either plus 1 or minus 1. So there are two roots of f dash x is equal to 0. One is x is equal to 1 and another is x is equal to minus 1. So at the value x is equal to 1 or minus 1, the function is either maximum or minimum. At present we don't know at which point the function is maximum or at which point the function is minimum. Only we know that at x is equal to 1 or and minus 1, the function is either maximum or minimum. Now let us see the second test or second step where we can come to know at exactly which point the function is maximum or it is minimum. So we find the second order derivative of the function fx. So let us differentiate once again the f dash x. So f dash x is 3x square minus 3. So if we differentiate this, we get second order derivative, that is f double dash x. So derivative of 3x square is 6x minus derivative of 3 is 0. So it is 6x. So this is second order derivative. Now we put the value of x is equal to 1 and minus 1 here in this second order derivative to confirm that at which point the function is minimum or the function is maximum. Now if we put x is equal to minus 1 here, so if we put x is equal to minus 1 here, we have 6 into minus 1, that is minus 6, which is less than 0. So it means at x is equal to minus 1, second order derivative is negative. So it means at x is equal to minus 1, the function fx is maximum. So here if we put x is equal to 1, that is second root, here we have 6 into 1, that is 6, which is greater than 0. So here we can say f double dash x at 1 is positive. So we can say that at x is equal to 1, the function fx is minimum. So here it is maximum at x is equal to minus 1 and it is minimum at x is equal to 1. So this test indicates at which root the function is maximum and function. X is equal to 1 and x is equal to minus 1 are called maxima and minima. They are known as maxima and minima. X is equal to minus 1 is maxima and x is equal to 1 is minima. Now let us find the maximum value of this function. To get the maximum value of the function, we put x is equal to minus 1 in the equation. So if we put x is equal to minus 1 here, it is minus 1 cube, that is minus 1 plus 3 plus 11. So 11 plus 3, 14 minus 1 is 13. This is the maximum value of the function. So the function gets maximum value 13 at x is equal to minus 1. Now if we put x is equal to 1 in this equation, we get 1 minus 3 plus 11, which is equal to 9, which is the minimum value of the function. So function gets value 9, that is minimum value at x is equal to 1. So this is the way how we can find the maximum value and the minimum value of the given function. First we differentiate the function with respect to x. We get the root of f dash x is equal to 0. For these roots we get the value of f double dash x. If the value is negative, we can say the function is maximum, and if it is negative, we can say if it is positive, we can say the function is minimum at that point. Now let us see one more example. Here we are asked to find the maximum and the minimum value of the function 2x cube minus 3x square minus 12x plus 5. So let us solve this example here. So the given function we solve it here. We are given fx, that is equal to 2x cube minus 3x square minus 12x plus 5. This is the function given to us, that is 2x cube minus 3x square minus 12x plus 5. Now we want the maximum value and the minimum value for this function. So what we'll do first, we'll find out f dash x is equal to 0. We'll find f dash x first. Now that is the first order derivative of this. Derivative of x cube is 3x square. So 3 into 2, that is 6x square, minus derivative of x square. Derivative of x square is 2x, so it is 2 into 3, so it is 6x, minus derivative of x is 1, so it is 12 into 1, that is, and 5 is constant, so its derivative is 0. So this is the first order derivative, that is f dash x of the function, that is 6x square minus 6x minus 12. Now let us find out the roots of this f dash x is equal to 0. So let us take f dash x is equal to 0 and we'll find the roots of this. So f dash x is 6x square minus 6x minus 12 is equal to 0. Now if we take 6 common, and 6 cannot be 0, so we can write x square minus x minus 2 is equal to 0. Now let us factorize this. There are two factors. One is x minus 2 and another is x plus 1. So we have two factors, x minus 2, x minus 1, because this is minus 2. So if we factorize it, that is minus 2 into 1, and sum of minus 2 plus 1 is plus 1 or minus 1. So this way. So it means x is equal to 2 and x is equal to minus 1. These are two roots. For this value, the function will be either maximum or it will be minimum. Now let us find at which point exactly the function is maximum or it is minimum. For that, let us find out f double dash x. So f double dash x is equal to 12x minus 6. Derivative of 6x square is 12x and derivative of 6x, 6 is constant, derivative of x is 1, so it is 12. Now let us get the value of f double dash 2. So f double dash 2 is equal to 12 into 2 minus 6 is 18, which is greater than 0, which is greater than 0. So at this 2, f double dash is positive, so we can say at x is equal to 2, fx is minimum. We can say at x is equal to 2, fx is minimum. And what is the minimum value for fx? So f of 2 is equal to 2 into 2 cube. If we put x is equal to 2, 2 cube is 8, minus 3 into 2 square is 4, minus, here if we take x is equal to 2, it is 24 plus 5. So it is 16 minus 12 minus 24 plus 5. So if we put x is equal to 2 here, we have 2 into 2 cube, that is 8. 2 square is 4, so it is 4. Here if we put 2, so 12 into 2 is 24 plus 5. So it is 16 minus 12 plus. So minus 12 minus 24 is minus 36, plus 16 is minus 20, plus 5 is minus 15. So 16 minus 12 is 4. If we add 4 here, it is minus 20, plus 5 is minus 15. So here the value of F2 is equal to minus 15, which is minimum value. So here we get the minimum value of the function. Now we are interested in the maximum value of the function. For that we put x is equal to minus 1 here in this. So f double dash is equal to minus 1. So if we put x is equal to minus 1 here, it is minus 12 minus 6 is minus 18, right? And it means f double dash minus 1 is equal to minus 18, which is less than 0. So at x is equal to minus 1, the function is maximum. So at x is equal to minus 1, fx is maximum. Fx is maximum. So here let us get the maximum value of the function. So it is f of minus 1, that is equal to 2 into minus 1 cube is minus 2, minus 1 square is plus 1 into 3, so it is minus 3. Minus 12 into minus 1 is plus 12 and plus 5. So it is equal to, this is minus 3 plus 3, sorry, minus 2 minus 3 is minus 5, plus 5 is 0, and the remaining is 12. So this is the maximum value of the function at x is equal to minus 1. So this is maximum value for the function. So let us have a brief look on what we have done. What we have done, we have differentiated the given function, that is this function, with respect to x, and we have substituted f dash x is equal to 0. We want to find out the roots. We got two roots, one is plus 2, another is minus 1. We have find out second order derivative, substituted x is equal to 2 gives the positive value, and hence at x is equal to 2 the function is minimum. And if you put x is equal to minus 1, we get negative value, so we can say that function is maximum at that, and we have find out its value. Now let us solve one more example. The function now here given is fx is equal to x plus 1 upon x. So the function given to us is x plus 1 upon x. Now let us differentiate it with respect to x. So f dash x is equal to 1 plus derivative of this is minus 1 upon x square. Derivative of 1 upon x. 1 upon x is x raised to minus 1, so its derivative with this. Now let us find the roots of f dash x is equal to 0. So if we put f dash x is equal to 0, we have this, that is 1 minus 1 upon x square is equal to 0. If we take x square LCM, we have x square minus 1 upon x square is equal to 0. It means x square minus 1 is equal to 0. So we got two root for this, x is equal to plus 1 or minus 1. So we got x is equal to plus 1 or minus 1, at which either the function is maximum or minimum. Now let us find the value of f double dash x at this point. For that, let us find out f double dash x. So f double dash x, for this f, if we differentiate this function, derivative of f dash x with respect to x is f double dash x. So we differentiate 1, will give 0, minus, if we differentiate 1 upon x square, it is minus 2 upon x cube. So this derivative is minus minus plus 2 upon x cube. So this is derivative, double derivative of fx. So we got second order derivative. Now let us find the value of f double dash at 1. So it is 2 upon 1 is 2, which is greater than 0. So f1 is minimum. f1 is minimum, or we can say at x is equal to 1, function is minimum. Now if we put the value in the function, we have f of 1 is equal to 1 plus 1 upon 1 is equal to 2. So that is the value of this. So what we have done, we have find out the root, get the second order derivative, that is the derivative of this, differentiation of 1, derivative of 1 is 0, minus derivative of 1 upon x square. So 1 upon x square is minus 2 upon x cube. So it is minus minus plus, so we have 2 upon x cube. If we put x is equal to 1, we have 2 upon 1 cube, that is 1. So it is equal to 2, which is greater than 0. And as we know, if double order derivative is greater than 0, the function is minimum at that. And if we put x is equal to 1 here, we have 1 plus 1 upon 1 is 2. Now let us find f double dash minus 1. So it is equal to 2 upon minus 1 cube is minus 1, which is minus 2 less than 0. So f of minus 1 is maximum. F double dash 1 is maximum. So here at x is equal to minus 1, the function is maximum. So if we put the value here, f of minus 1, it is minus 1 plus 1 upon minus 1, so it is minus 2. So this value is maximum value for this. So we got the minimum value and the maximum value of the function for fx is equal to x plus 1 upon x. This is the way we can get the maximum and minimum for the given function. Let us have one more example here. So here the function we have taken is x into log x. The function we are taking x is equal to log x, and we are interested in the maximum and minimum value for this function. For that, we will first find the first order derivative of the function. So f dash x is equal to derivative of x is 1, at that time log x remain as it is, plus log x remains as it is into derivative of log x is 1 by x. So it is log x plus 1. It is log x plus 1. So this is f dash x. Now if we find the roots of f dash x, is equal to 0, we have log x plus 1 is equal to 0. So log x is equal to minus 1. So x is equal to e raised to minus 1. X is equal to e raised to minus 1. So if we get the value of x, log x is equal to minus 1, we have x is equal to e raised to minus 1. Now here we are getting only one value for which either the function is maximum or the function is minimum. So here we will get either maximum or minimum. Let us see what we are getting. So let us differentiate this function once again. So let us differentiate f dash x with respect to x once again. So derivative of log x is 1 by x plus derivative of 1 is 0. So here we are getting f double dash x is equal to 1 upon x. Now if we put here x is equal to 1 upon e, we have 1 upon 1 by e, which is equal to e, which is greater than 0. So what it means, that function fx is minimum at x is equal to 1 upon e. So here we are getting only minimum value for the function, not the maximum value. So here we can say that this function has only minimum value, it has no maximum value at all, and the minimum value for this function is f of 1 upon e is equal to 1 upon e into log of 1 upon e. Log of 1 upon e is minus 1, so it is minus 1 upon e. This is the minimum value for the function. So sometimes it may happen that we only get the minimum value or a maximum value of the function. Each time it is not necessary to get the maximum or a minimum, both value simultaneously. This is one example where we got only a maximum value of the function. Let us have a look on one more example, that is the maximum, to find the maximum or the minimum value for sin x plus cos x. Here we are taking the trigonometric function. Previously we have taken a polynomial, then a logarithmic function. Now we are taking trigonometric function. So for each type of function we can find the maximum or a minimum value of a function. The procedure is same. First we'll find f dash x. So f dash x is derivative of sin x is cos x, and derivative of cos x is minus sin x. So let us find the root of f dash x is equal to 0, that is cos x minus sin x is equal to 0. So we can say cos x is equal to sin x, or we can say tan x is equal to 1. Now tan is positive in either first quadrant or in third quadrant, so we take so many values for these x for which either the function is maximum or minimum, or it has tan x is equal to 1. For that, let us put the restriction on x, that is, say x lies between 0 to 2 pi. So let us discuss only the maximum and minimum value for, because there are infinitely many points at which, or x for which the function tan x is equal to 1. So for 0 to 2 pi, only first and third quadrant in which tan x will become positive. So one value for x is pi by 4 and another value is 3 pi by 4, that is pi minus pi by 4. So for these two values, the function tan x will get value 1. So these are the roots of f dash x. The roots of f dash x. Now let us find the second order derivative, that is f double dash x, which is equal to derivative of cos x is minus sin x minus derivative of sin x is cos x. So this is second order derivative of this function. Now first we'll put f double dash x. Put x is equal to pi by 4. So if we put x is equal to pi by 4, we have minus sine pi by 4 minus cos pi by 4. As we know, the value is minus 1 upon root 2. So it is minus 1 upon root 2 upon minus 1 upon root 2. Both are negative, so which is less than 0. There is no need to calculate, it is less than 0. So at x is equal to pi by 4, fx is maximum. It has maximum value at x is equal to pi by 4. What maximum value it will obtain is pi by 4 is sine pi by 4 plus cos pi by 4. So what exactly we are doing? We put x is equal to pi by 4 in the given equation, that is 1 upon root 2 plus 1 upon root 2. So it is 2 by root 2. So it is root 2. So this is the maximum value for the function at x is equal to pi by 4. Now if we put x is equal to 3 pi by 4 in second order derivative, we have minus sine 3 pi by 4 minus cos 3 pi by 4. As we know that 3 pi by 4 is in the third quadrant, and in third quadrant both sine and cos are negative, so minus minus plus 1 upon root 2 and this is plus 1 upon root 2. The value of sine 3 pi by 4, sine 3 pi by 4 is minus 1 upon root 2, because in the third quadrant it is negative. So the value is negative, it has a negative sign here, so minus minus plus. So it is 2 upon root 2. So it is root 2, which is greater than 0. So we can say at f double dash 3 pi by 4 is positive. So at x is equal to 3 pi by 4, the function is minimum. The function is minimum. So here the function f 3 pi by 4 is equal to sine 3 pi by 4 plus cos 3 pi by 4. What exactly we are doing? We substitute the value of x is equal to 3 pi by 4 in this equation. As we know, this at x is equal to 3 pi by 4, the function is minimum. It is minimum. So here we put the value of this, it is minus 1 upon root 2 minus 1 upon root 2. So it is minus root 2. Right. So this is minimum value of the function at this. So this way we can find the maximum and the minimum value of the function sin x plus cos x. So we have here maximum and minimum value of a trigonometric function. Here we are confining our range of x because we know that sine and cos are periodic functions, so we may get so many values at which the function, or infinitely many values for which the function is either maximum or minimum. So we have take the restriction on x. We have only taken the value of x between 0 to 2,5 for this example, and we got two value, that is pi by 4 and 3 pi by 4 in first quadrant and third quadrant. So we got the maximum. And here we have some exercise for a calculation. We have to find the maximum and minimum value for such type of function, that is fx is equal to 3x cube minus 4x square minus x plus 5, x cube minus 6x square plus 9x plus 15, then x plus 4 by x, and finally x square plus 4x minus 5 plus 3. In each of the example we have to find out f dash x, and then the roots of f dash x is equal to 0. Then we get the f double dash x. We put the value of this roots in f double dash x and find whether it is positive or negative, and then if the value is negative, we can say the function is maximum, and if it is positive, we can say the function is minimum. Let us solve one example out of this. So let us say solve the first example, that is fx is equal to 3x square minus 3x cube fx is equal to 3x cube minus 4x square minus x plus 5. So here it is 9x square. F dash x is 9x square minus 8x minus 1. So here we are getting first order derivative, that is 9x square minus 8x minus 1. Now if we take f dash x is equal to 0, we have 9x square minus 8x minus 1 is equal to 0. So let us factorize this. So 9x square minus 9x plus x minus 1 is equal to 0. So if we take 9x common, we have x minus 1, and if we take 1 common, we have x minus 1. So x minus 1 is one factor, and another factor is 9x plus 1 is equal to 0. So x is equal to either 1 or x is equal to minus 1 upon 9. So these are 2 points for which the function is either maximum or a minimum. Now if we find f double dash x, here we get derivative of 9x square is 18x minus 8. Now if we put x is equal to 1 here in f double dash x, we have 18 minus 8 is 10, which is greater than 0. So we can say at x is equal to 1, fx is minimum. Fx is minimum. And the minimum value can be obtained if we put x is equal to 9 here. So f of 1 is equal to whatever we get is a minimum value. I leave this for you for practice. Now if we put x is equal to minus 1 upon 9, it is equal to 18 into minus 1 by 9 minus 8 is minus, this is minus 2, minus 8 is minus 10, which is less than 0. So at x is equal to minus 1 by 9 function is maximum, and f minus 1 by 9 is the value which is maximum value, So this way you can guide. This also I leave for you to practice. So you try to work out the maximum and minimum value for this. Remaining 3 examples you try yourself, and much more examples you can have to practice, so that you can get a good idea and a very proper understanding of this topic. This is one application of maxima and minima for differentiation. One more application we'll see next time, that is the velocity and acceleration. Thank you.